So we have seen that there are several types of convergence of random variables. One of them is weak law of large numbers, which explores behavior of a random variable in the sense of probability, or we define it as a convergence with respect to probability or convergence in probability. Similarly, we have already defined, and we know that there is another very important type of convergence, which is actually almost sure convergence or almost everywhere convergence. So we have defined this almost sure convergence, but till now we did not study any such theorem or any such particular result which really explores this behavior, or under what are the characteristics of this kind of convergence. Is there any condition under which we can say that, well, this a particular sequence of random variables will converge to another random variable almost surely. So all this will be studied today in terms of what is known as strong law of large numbers, and more specifically this strong law of large numbers is mainly due to Kolmogorov. So today we will study this strong law of large numbers, or Kolmogorov's strong law of large numbers, in detail along with the detailed proof. We should start with the definition of almost sure convergence. We have already defined it, but just to give a formal definition, a sequence xn n greater than equals to 1 of L1 random variables, that means whose expectation exists, is said to obey the classical strong law of large numbers, or in brief SLLN, if we can establish that 1 by n summation I equals to 1 to n xi minus expectation of xi, this goes to 0 almost surely. So this is a very definition and very formal definition of almost sure convergence, or rather very formal definition when a sequence of random variables follows strong law of large numbers in terms of almost sure convergence. To this end, Kolmogorov's actually proposed one strong law of large numbers for independent random variables. The way we can establish, or we can present this formal SLLN due to Kolmogorov, is that suppose x1, x2, xn be independent random variables where expectation of xk equals to 0 for every k greater than equals to 1, and summation I n equals to 1 to infinity expectation of xn square divided by n square, that is less than infinity. So under these two conditions, it can be shown that Sn by n goes to 0 almost surely as n goes to infinity, where naturally Sn is the sum of random variables, that is summation xi I equals to 1 to n. Kolmogorov also proposed another strong law of large numbers for identically and independently distributed random variables. So here the identical condition comes into the picture, that x1, x2, xn be independent random variables, and if we write Sn by n equals to summation xi by n, then we can show that Sn by n converges to C, where C is a finite number almost surely if and only if expectation of modulus x1 less than infinity and C equals to expectation of modulus of x1, because since expectation of modulus x1 less than infinity, we can easily say that this must be equals to a finite number which we call as C, and incidentally Sn by n converges to this C almost surely provided expectation of mod x1 less than infinity. This is nothing but Kolmogorov's strong law of large numbers for IID random variables. Now we are going to prove this result, but before that let us recall a few more results. One, the most important, is that called Moment's lemma due to Loew, which states that if x is a random variable and we define qt as probability modulus of x greater than t, which is equals to 1 minus ft or f bar t, then for every r greater than 0 and x greater than 0, we have this inequality, that is x to the power r summation n equals to 1 to infinity q of n to the power 1 by r x less than equals to expectation of modulus of x to the power r less than equals to x to the power r plus x to the power r into summation n equals to 1 to infinity q into n to the power 1 by r x. Now note that here this moment actually gives us a lower and upper bound of expectation of mod of x r where r is greater than 0, that means for any r positive. So this is a very important theorem, important lemma. This gives us that the moment is bounded by some functions of the probability, or rather f bar t or qt. Another important result which we have already discussed, which is known as Borel-01 law. This is related to the sequence of independent events. Let omega script b and p be a probability space and an be a sequence of independent events. This independence is very important. Then it can be shown that probability an occurs infinitely often equals to 0 if and only if summation probability of n equals to 1 to infinity less than infinity. So these two results, one is Borel-01 law and one other is Moment's lemma. We are going to use these two in proving Kolmogorov's strong law of large numbers. So let us make a quick statement that of this law, let x1 x2 xn be a sequence of IID random variables, then Sn by n goes to c less than infinity almost surely if and only if expectation of mod x1 less than infinity and c equals to expectation of mod x1. Now we are going to prove this result. First we will concentrate on the only if part. Suppose let us define an event an as modulus of x greater than equals to n for n greater than equals to 1. Now use Moment's lemma and put x equals to 1 and r equals to 1, then immediately we can get summation n equals to 1 to infinity probability of an is less than equals to expectation of mod x1 less than equals to 1 plus summation n equals to 1 to infinity probability of an. That means expectation of modulus of x1 is bounded by sum of probabilities. Both upper bound and lower bound can be obtained through Moment's lemma. It's just a direct application of Moment's lemma for a particular value of x and r. In this case, both are equal to 1. Now let us look at this event an little more carefully. So we see that probability of an equals to probability of mod x greater than equals to n. That's the way we defined. Now we have assumed that x1, x2, xn are a sequence of IID random variables. So we can immediately write, instead of x, we can immediately write x1. So probability of modulus of x1 greater than equals to n. Now if Sn by n converges almost surely to c, which is less than infinity, that means this is the only if part. So we have assumed that if we can assume that Sn by n converges to c almost surely. C is a finite number. Then we can write xn by n, which is equals to Sn by n minus n minus 1 by n into Sn minus 1 by n minus 1. Here it is clear that this n minus 1 and n minus 1 cancels each other and we are left with Sn minus 1 divided by n. Now the numerator is nothing but xn because Sn is sum of xi's I equals to 1 to n. And since Sn by n converges to c almost surely, it is immediately clear that the first part, that is Sn by n, goes to c, and the second part Sn minus 1 by n minus 1 also goes to c, whereas n minus 1 by n goes to 1. So in effect xn by n goes to c minus c, which is equals to 0 almost surely. So which immediately implies that probability modulus of x1 by n greater than equals to half. Since it goes to 0, we can just say that it is greater than equals to half, some number infinitely often is 0. Hence just using Borel-01 law, we can immediately say that summation probability n equals to 1 to infinity probability of modulus of xn greater than n by 2 is less than infinity, which indicates immediately that summation n equals to 1 to infinity probability modulus of x1 greater than n by 2 is also less than infinity, because these random variables are IID. So we can easily replace xn by just x1. Now, so we have this result that summation probability mod x1 greater than n by 2 less than infinity. Now recall the previous result that we have just shown, that the bound of expectation of modulus of x1. Here summation, now this expectation of modulus of x1 is bounded by sum of probabilities, which is in fact summation n equals to 1 to infinity probability of an, which is less than equals to summation n equals to 1 to infinity probability modulus of x1 greater than equals to n by 2, which is less than infinity. Just by using Borel's 0-1 law we have immediately shown. So we can have expectation of modulus of x bracket x1 is less than infinity. So the only part is proved. That means all we have to show the finiteness of the first order moment or first order absolute moment, which is already proved now. Next, the if part. Now the proof of if part is little bit technical, but it's very interesting. So let us go through this proof very slowly. Suppose expectation of mod x1 less than infinity, because this is the if part, so we know that expectation of x1, we can assume that expectation of mod x1 less than infinity, and let's say expectation of x1 equals to c. Now we define a new random variable. Let's call this new random variable as xk star, which is equals to x into indicator function over the set modulus of xk less than equals to k. And we define this xk star variable for k equals to 1, 2 and so on. And naturally we can define the sum of these random variables up to n, that is x1 star plus x2 star plus xn star, as Sn star. Then it is clear that we know that x1, x2, xn, they are all independent random variables. They are IID, but also they are actually independent. So we are just using this independence part here. So clearly xk star k equals to 1 to n are also independent random variables with modulus of xk less than equals to k. And this implies that modulus of xk star is also less than equals to k. Now using Moment's lemma again, and noting that or denoting ak equals to modulus of x greater than modulus of xk greater than n, we can immediately write that summation k equals to 1 to infinity probability xk not equals to xk star. Now note that xk star is defined in terms of xk only when xk is modulus of xk less than equals to k. So the set on which xk not equals to xk star is actually the set when modulus of xk greater than k. So probability xk not equals to xk star is nothing but summation k equals to 1 to infinity probability modulus of xk greater than k, which is less than equals to summation k equals to 1 to infinity probability of ak, if we recall the definition of ak here. And again by Moment's lemma, this is bounded above by expectation of mod x1. Now mod x1 is less than infinity, we have already assumed. So what we have, summation probability xk not equals to xk star is less than infinity. Hence we can immediately use Borel-Cantilly lemma to show that probability xk not equals to xk star occurs infinitely often equals to 0. Now this is a simple application of Borel-Cantilly lemma. So which immediately says that Sn, that means whenever xk not equals to xk star that occurs infinitely often, that probability of that event equals to 0, which means that Sn minus Sn star by n goes to 0 almost surely as n goes to infinity. That means it is clear that Sn by n and Sn star by n converges to the same limit almost surely, provided they should converge, provided they converge at all. So now it is enough to prove that Sn star by n goes to expectation of x1, which obviously less than infinity. Now note one important thing, that we have started with the sequence of random variables x1, x2, xn, and they are all independently and identically distributed. But here this xn star the way we define this new random variable from xn, they are actually independent but not necessarily identically distributed. So, this is a very important thing that we should note, that we are losing that identically distributed condition in here for the sequence xn star. So, all we have to show, actually we have to show two things. One is expectation of Sn star by n goes to expectation of x1, which is equals to c, and 2 summation n equals to 1 to infinity variance of xn star by n square less than infinity. It is clear that the second condition implies that Sn minus Sn star by n goes to 0 almost surely. So, it is enough to show only these two conditions now. Now, remember one thing, that these two conditions are with respect to xn star, the newly defined random variables from the IID distributed random variables xn. Let us see what is expectation of xn star. Now, expectation of xn star equals to expectation of, let us write down xn star. This is xn into indicator function of over the set modulus of xn less than equals to n. Again, xn's are IID random variables, so we can replace this n by 1. So, we get expectation of x1 into indicator over modulus of x1 less than equals to n. And as n goes to infinity, that means this modulus of x1 less than equals to n, as n goes to infinity, basically this represents the entire random variable x1 over the entire support. So, this entire quantity converges to expectation of x1 almost surely. That means here we prove that it is very easy to see that expectation of xn star converges to expectation of x1 almost surely, which immediately implies that expectation of Sn star by n converges to expectation of x1 as n goes to infinity. So, the first part is proved. Now, the proof of the second part starts with just writing the condition, that is summation n equals to 1 to infinity variance of xn star by n square, which is less than equals to 1 by n square, summation n equals to 1 to infinity expectation of xn star square. This is just from the relation between variance and expectation of x square, which is equals to, we can write expectation of xn star square in a different way. It is a very nice way to look at this expectation of xn star. In fact, one can write expectation of any quantity in this form, that is summation n equals to 1 to n 1 by n square into integration over mod xn less than equals to n xn square dp, which is equals to summation n equals to 1 to infinity 1 by n square summation k equals to 1 to n k minus 1 mod xn less than equals to k xn square dp. So, here we are first using the definition of xn star in terms of xn, and then we are splitting the set modulus of xn less than equals to n for every k equals to 1 to n. We are splitting this set into small pieces. Then, so this has become just a double summation k equals to 1 to infinity n equals to k to infinity 1 by n square integration k minus 1 less than mod x1 less than equals to k x1 square dp, because we know that xn sequence x1 x2 xn, they are all IID random variables. So, we can immediately replace xn by x1. Now, we know that whenever we get two summation notations, we can use one technique, that is change of the order of this summation, and to do that we can easily do that. And another important thing is that here 1 by n square is there and k n equals to k to infinity. So, just doing simple algebra, we can get an upper bound, that is less than equals to summation k equals to 1 to infinity 1 by k square into probability k minus 1 less than mod x1 less than equals to k, which is nothing but summation k equals to 1 to infinity k times probability k minus 1 less than mod x1 less than equals to k. And immediately we can just write this entire quantity as equals to, just by changing this k equals to 1 to infinity, just doing certain kind of change of variable, we can write k minus 1 into probability k minus 1 less than mod x1 less than equals to k plus 1, which is less than or equals to summation k equals to 1 to infinity integration over k minus 1 less than mod x1 less than equals to k x1 dp plus 1. Now, this first term is nothing but expectation of mod x1. So, eventually this summation variance of xn star by n square is less than equals to expectation of mod x1 plus 1, and by our assumption expectation of mod x1 is less than infinity, that is the given. So, this entire quantity summation variance of xn star by n square, which is actually now less than infinity. So, that completes the proof of this strong law of large number. So, we have seen the statement and proof of Kolmogorov's strong law of large numbers, that is Kolmogorov's SLLN as it is abbreviated commonly. This proof really involves some amount of elegance as far as the technique of the proof is concerned. We have seen that how we can break down a particular event in terms of and how the tail probability comes into the picture just by breaking down the event. And since the tail probability or some kind of tail events comes into the picture, so naturally Borel-01 law or Borel-Cantelli lemma is extremely important, and we have used this thing as we needed. We have also seen that there is some kind of relation with the expectation of the random variable for which we are trying to investigate this is almost sure convergence. So, naturally the question will come that whether what is the role of this expectation or under what condition this exists, and all this there are some other questions that will naturally come into our mind. So, we will all investigate these questions in our next lectures, in the future course of lectures. But as of now, this is the proof of Kolmogorov's strong law of large numbers, and which is extremely important in studying the behavior of a sequence of random variables as n goes to infinity. Now, remember that this behavior is in the sense of almost sure convergence.